Alright, this is 3.1 physics. Talking about light. Light is weird. Yeah, I don't want to talk about it, but I have to. Let's go. I like that freestyle. What do you think? The first thing is transmission of waves. Well, let's say radio waves. The wave you use to, listen to music, you put on your car. Radio uses radio waves. Pretty straightforward. And radio waves are produced by an antenna. They're also received by antenna. They are a type of electromagnetic waves. And what electromagnetic waves is just a type of wave, like water wave, right? But it's using a different medium. Let's say water wave is using water as the medium. Sound wave would be using the air, depending on how you're making the sound, like where you're making the sound. And the electromagnetic wave is using the electric and the magnetic field. But different to the other waves, electromagnetic waves have two planes. Uh, let's say using the example of a radio, right? On one plane we can have the electric plane, the electric field. So this will be propagating vertically. We will call this having a vertical plane because it's going up and down, up and down, up and down. Now the other plane is 90 degrees to this vertical plane. So it's gonna be horizontal. This is kind of hard to represent on a side view. But if we have to, we can just do it like this. So 90 degrees to the electric field, we have the magnetic field. We can better represent this using a bird eye view. Let's say from the top, this time you have the propagating one is the magnetic field. And in black, you can have the electric field. This one's going up and down, up and down, up and down. Now we use the word plane of polarization to describe the direction that an electromagnetic wave is oscillating at. Oscillating just means vibrating. But you're like, it has two planes, so which one is it? Well, we use the electric field as the plane of polarization. So when we say an electric field is propagating vertically, what we're really saying is its electric field is propagating up and down vertically. And this relates to the receiving and producing of radio waves using antenna. Let's say you have an antenna that emits, well, actually, we can use the same diagram. Sorry. Whoops. What the heck? That's all right. It's vertically propagating. Right, the electric field is vertically propagating. Now, to be able to receive this antenna, the receiving antenna has to be placed in a certain way, such that it can receive this vertical electric field, electromagnetic wave. So, in summary, the receiving antenna has to be placed in the same, well, like the placement, like in a way that they can produce and receive electromagnetic waves of the same plane. So that's transmission of wave. Secondly, you have three types of light: coherent, monochromatic, and incandescent. So coherent light just means you have all light on the same frequency. And what this means is they're going up and down, they're propagating at the same rate. They're propagating at the same rate. But you can have what you can have is coherent light that have uh, a, a phase difference. Phase difference just means, well, let's use example. The trough on this wave is right here. Now the trough on this wave is kind of behind the trough on this wave. So you can say that this one is the wave on top is kind of shifted forward by a tiny bit than the wave on the bottom. And when we are saying the phase difference, we are talking about the distance between these 2 points. The same points on the wave, they're the same points on the wave, both the troughs, but there's a difference in their phase. But when we move to the next trough, say, and you measure the phase difference again, if I draw this perfectly, you'll find out they are constant. And when this happens, we describe the two waves as having a constant phase difference or a constant phase relationship. And we can call such light coherent light. Then you also have monochromatic light. This one is easier to explain because, um, oof, that's pretty bad. All right, there you go. So monochromatic light is just light of the same frequencies, but there's no phase difference. There's no phase difference between them. When this one is at the trough, so does this. When this one is at the, I mean, sorry, let me say again. When this one is at the peak, so is this one. When this one is at the trough, so is this one. And you can tell this goes on, and we call such light monochromatic light. An incandescent light, which is a light caused by random vibrations or heating up, is not coherent or monochromatic. Incandescent light is quite common. We see it every day. If you have incandescent light bulb, that is the power consuming light bulb, and it heats up and gets quite hot. That's the incandescent light bulb, and it releases incandescent light. So does our sun. Our sun produces light as a result of heating up. So the sunlight is incandescent. And you also have, let's say, the fireplace, right? The coals, as a result of heating up, they produce a dark, warm red color. And that would be incandescence or molten lava. And you can find so many examples of this in nature and man made incandescent light. So, why isn't incandescent light monochromatic or coherent? The reason is, to simplify this, the reason is incandescent light is made by random vibrations, right? Because heating is just random atom vibrations. So random vibrations would just create random frequency of light that don't maintain a constant phase relationship with each other. So what you get is just a mix of a light of all frequencies, and it gets pretty messy the more you do it, right? Gets messy. Okay, you get the point. So incandescent light is not monochromatic or coherent. Now, talking about the phase difference, we can talk about constructive and deconstructive interference. So, constructive interference is essentially when you put two waves that have a phase difference of a whole number. That means is that they line up, right? All the points on this wave line up. They sync up with each other. When this one is at the peak, this one is at the peak. When this one is at the trough, that one's at the trough. What you get when putting these two waves over each other is a combined wave, and the resulting wave will have a magnitude of these two waves combined. So let's say the magnitude of this is 1, right? 1, 1. And the magnitude of this is 1, also 1. What you get is a wave that goes twice as high, and twice as low, and twice as high, and twice as low. So that would be constructive interference. But deconstructive interference is the complete, well, opposite, you can say that. So this is when the waves are shifted by half a wavelength. Thus, you get a trough, and on the other wave, you get a peak. And they are the same magnitude. So when this happens, all the points on the two waves perfectly cancel out to make nothing. Nothing, absolutely nothing, just a flat line. You can't see it, you can't hear it, there is no wave. And some of the noise canceling headphones use this. They detect the environmental noise and they play a sound. They actually play a sound to cancel out that environmental noise. So you just get this really quiet environment. So I think that's pretty cool. Alright, the last one is double slit experiment. And you need to be able to derive the formula d sine theta equals m lambda, and we're going to do that right now. So what you have is a double slit. Now I draw them very wide, and you do. But in reality, they're very thin slits, right? These two are like super thin. And what you do is you shine a monochromatic light through the two slits, and they diffract, right? After they diffract, we say they reach just a random point on the wall. So light from this slit will go there, and the light from that slit will reach there. And you can tell that this light has to travel less distance to get to that point than this light has to. And there's a difference between how long they travel, how much distance they travel, and we call that the phase difference. The phase difference. Sorry, not the phase difference, the path difference. And we know it's always m lambda because it's always a constant times the wavelength. And what we also know is the slit separation, so the distance between the two openings. We use d to represent the slit separation. And what we do next is draw a larger triangle like this. This one, we don't need to know why, but we just need to know that this large triangle here is proportional to the small triangle right here. So if you just flip this around so that they are placed next to each other, they're actually proportional. So we can use this small triangle to do calculations with the large triangle, and we're gonna go into that. So where does d sine theta comes from? To do that, we need one more information, is that the angle, right? The angle theta of the small triangle. So now we know the angle, the and two sides, and that the triangle is a right angle triangle. We can use the SOHCAHTOA rule. So we have the opposite side, we have the hypotenuse side. So we use SOH. So that's sine theta equals O over H SOHCAHTOA. And then we get sine theta. Look up, what's the opposite side? Okay, it's the m lambda over d. Rearrange to get d sine theta equals m lambda. And that's how you derive it. No math, just pure diagram.